Okay, so we're looking again at approximating the binomial distribution to the normal distribution. The conditions that will allow us to make a good approximation is that the value of n from the binomial is large and the value of p is close to 0.5. So we can actually see here that yes, n is indeed large, is 150, and the value of p is close to 0.5. So this would work as a good approximation. On this example, it's already been approximated for us, but let's just follow through and make sure we know how to get those values. For the normal distribution, I need to know the mean. And I'm talking about mu, so the population mean. And that can be estimated using n times p, which in this case is going to be 150 times 0.48, which does indeed lead to 72. We're also going to need to know the standard deviation for the normal distribution, which we can find by taking the square root of the variance of x. In the binomial, the variance was calculated by doing n times p times q, where q is the probability of failure. You can refer to it as 1 minus p. Alright, so calculating that, we get 150 times 0.48 times 0.52, which is 6.12 to 2 decimal places. Okay, don't forget that's the standard deviation, so as we write the distribution, we'll write it with the squared to make sure we're representing the variance. Okay, so those things have been approximated and we're confident that we know how to produce those for ourselves. Let's go ahead and respond to these questions. So A, probability that A is less than or equal to 70. Okay, remember that when we then move to the normal distribution, we need to apply a continuity correction. The binomial is a discrete distribution, the normal is continuous. Whenever you go from a discrete to a continuous, continuity correction is necessary. So what that means is that I'm not going to stop at exactly 70 because there's a massive gap. I say massive, there's a gap between 70 and 71, and I just need to close that gap in terms of my continuity correction. It's going to be a 0.5 difference from 70, and to make sure that you always get it correct, think of including the number 70. If I put less than or equal to 69.5, this inequality does not include the number 70, so that's a quick check to show that that is incorrect. I'm going to need to go to 70.5. Everything that's less than or equal to 70.5 will include the value 70, so we're good to go. Because at this point we just need to put it into our calculator. We get 0.4032. That's to the 4 decimal places. We like 4 decimal places in stats. And this is an approximation, so it's approximately equal to this answer. Okay, looking at part B. Okay, so once again, we need to make sure that we apply a continuity correction and just be smart about which values we're going to include. I'm originally thinking of all the values in between 80 and 90. 80's included, 90's not. Let's actually rewrite this so that I'm only thinking about the values that are included. Okay, so that's an equivalent probability statement, which is approximately equal to all of the numbers in between 79.5 and 89.5. So let's just have a think of this. If I start at 79.5 and go for the numbers bigger, will I include the number 80? Yes. And if I go all the way up to and stop at 89.5, will I have included the number 89? Yes, I will. Okay, so once again, at this point, we're ready just to punch this into the calculator. 0.1081 to 4 decimal places. Okay, that's the answer that I get if I put in 6.12 for my standard deviation. But I do notice using the answer button gets you a slightly more accurate answer of 0.1080. The mark scheme will allow for different levels of accuracy. Putting or using the entire value, so using your answer button, will always be the more accurate of the available answers. Okay, so for a particular type of bulb, 55% will produce yellow flowers. A random sample of 80 bulbs are planted. Calculate the percentage error incurred when using a normal approximation to estimate the probability that there are exactly 50 yellow flowers. All right, so just to see how good an approximation we might be able to make, let's try and answer this question using the binomial and then using the normal approximation. All right, so x follows a binomial distribution where n equals 80 and p equals 0.55. What is the probability that we get exactly 50 of those yellow flowers sprouting? Okay, so putting this into your calculator, 0.0365 to 4 decimal places. How would it differ if we'd gone for the normal approximation? Okay, so y follows a normal distribution. To calculate mu, I'm going to do NP. To calculate mu, which is the expectation of x, we're going to go ahead and calculate NP. In this case, that's 80 times 0.55. This is the answer of 44. And we're also going to need to find our standard deviation. Okay, and that gives us the square root of 19.8 to 3 significant figures. And that gives us our 19.8. Okay, so I've got my standard deviation and I've got my mean. Let's state this distribution. So y follows a normal, with a mean of 44, standard deviation of 19.8. Okay, our probability statement, we're going to need to apply continuity correction. So I want an interval that's going to include the number 50, start at 49.5, up to 50.5, and that will include the number 50 for us. This, just straight into our calculators, gives us 0.0362. Okay, so those two answers are actually very similar. What's the actual percentage error? By what percent is our approximation off? So let's just quickly do that calculation. So the binomial result minus the normal result all over the original or the more accurate answer, 0.0365. Plug it into the calculator, 0.0082. All right, so that's 0.82%. So the binomial approximation on some good criteria, good conditions, we're not very far off from the accurate or the original answer. Okay, so hopefully that will increase your confidence in using the binomial approximation in responding to certain questions.